Hi everyone, this is Zhenyang Tang. Today I'm happy to share you with our work MathScale Scaling Instruction Tuning for Mathematical Reasoning. Large language models have demonstrated remarkable capabilities in mathematical problem solving. One driving force behind the success is instruction tuning. Unfortunately, this approach is constrained by the limited size of existing datasets. For example, the most popular math datasets GSM8K and MATH each only contains around 7.5K training examples. So researchers has proposed to augment existing datasets by using frontier large language models. For instance, Wizard Math introduced several operations to generate math questions with increased complexities. However, the newly generated examples by these methods exhibit substantial similarity to the original example, as can be seen in the example of MetaMath. Therefore, it will limit their power in generating large-scale math datasets. In this work, we ask, can we figure out a method that reduces dependence on original training examples while generating high-quality mathematical data on a much larger scale? We therefore propose a conceptually simple and scalable method, MathScale, as can be seen in the pipeline. It is less dependent on the original training examples. Specifically, it first prompts GPT 3.5 to extract high-level concepts such as mathematical topics and knowledge points. Given these extractions, we then build a concept graph, which is used to estimate the connections between different concepts. Finally, we can instruct GPT 3.5 to generate new math questions based on the sampled concepts from the graph. Intuitively, we can generate significantly more examples using different combinations of the concepts, some augmentation-based methods. Our method also bears resemblance to the cognitive mechanism in human mathematical learning. It argues that the learning process consists of two steps. One is concept compression and the other is connection forging. Concept compression actually mirrors our high-level concept extraction, while connection forging is similar to our concept graph construction. Now, let's dive into MathScale. For the first step, concept extraction, as can be shown in this prompt template, we ask GPT 3.5 to act as a math teacher and extract high-level concepts such as topics and knowledge points from seed questions. Here, a topic usually refers to the mathematical subject name or the topic name of a math book chapter. For example, money and finance or arithmetic operations, while knowledge points usually refers to more fine-grained math concepts. For example, theorems and scales. As shown in this figure, such as definition and properties of dot product or manipulation of complex numbers. Given the topics and knowledge points extracted, we can move on to construct a concept graph, whose nodes are those extracted topics and knowledge points. There are three types of edges. One is topic to topic, another one is topic to knowledge points, and finally the top knowledge points to knowledge points. Their edge weights are determined by the statistics of co-occurrences. Given the graph constructed, we can sample topics and knowledge points using a graph random walk algorithm. The newly created concept composition can be used to create new math questions subsequently. So here are our prompt. We ask GPT 3.5 to act as math teacher again to generate new question and solution based on sampled topics and knowledge points. We also want to mention that we include few short examples chosen from the seed question based on Jakarta distance of knowledge point sets. And here is an example of our generated data. As we can see, it tries to find the rank of a matrix, and the solution is completely right. After this step, many of us would be concerned of the validation of generated data. We also do some small scale experiments, but we find that validation does not improve the results. Therefore, we remove this validation step in our final pipeline. Interesting reader can refer to our paper. So, in summary, our work actually aims to create a much larger scale math dataset by leveraging the important role of math concepts compared to augmentation-based methods. For our main experiment, we prompt GPT 3.5 for the whole pipeline of MathScale, resulting in 2 million training data points. We call the data MathScaleQA. We wrapped questions in Parquet template as prompt and treat answers as completions. We then fine-tune open source LLMs on it. For evaluation, we introduced MwpBench. It's a benchmark of math word problem, including 9 datasets across K-12, college, and competition math such as college math, TAL, MwpBench, and SAT, etc. As shown in this table, MathScale obtains best micro and macro averages across MwpBench compared to all other open source models. Specifically, for MathScale 7b, fine-tuned on LLaMA-2 7b, MathScale achieves 35.2% micro and 38.2% macro accuracy, surpassing all its best peers significantly. This trend is also similar for MathScale 13b, fine-tuned on LLaMA-2 13b, and MathScale Mistral, fine-tuned on Mistral 7b. This also confirms the effectiveness of our MathScaleQA dataset, regardless of the backbone model. When compared to frontier large language models, as we can see, MathScale Mistral actually performs quite closely with GPT 3.5. We further compare with WizardMath and MetaMath under the same or less training sets. As we can see, MathScale 7b consistently achieves better results on most datasets, as well as both micro and macro accuracies. We also want to highlight the scaling property of MathScale. Given the fixed set of math concepts, iterating over concept graphs allows us to generate even more different concept composition, thereby synthesizing even larger amount of new math data. We use LLaMA-2 7b as our base model. As we can see, when we scale the size of MathScaleQA dataset, we observe a nearly logarithmic growth in the performance across all datasets within MwpBench. We also compare MathScale against WizardMath and MetaMath at their respective training sets. Given the scaling curve in this figure, we anticipate that the performance of MathScale may continue to improve with even more synthetic training examples. Due to resource constraints, we leave this to future work. Finally, we also conduct extensive ablation experiments to confirm the effectiveness of MathScale pipeline. As we can see, remove any step will result in a performance drop in the left table. While MathScaleQA is rigorously deconcatenated to prevent overlap with downstream test data, we understand that there may be still some concerns of data leakage. To address this concern, we manually curate a new dataset comprising 13 math questions from latest Gaokao math held in June for China National Higher Educational Entrance Examination. We can see that MathScale consistently surpassing its best peers. It demonstrates the robustness of MathScale in handling fresh math questions. Okay, this is it. Thanks for your watching. If you are interested in our work, feel free to follow us and drop any questions. Thanks.